One question you might ask is, how do you find prime numbers? Well, there is an algorithm that was developed a long time ago for finding prime numbers, and I want to explain it. But first, I want to establish an idea. So let's suppose you have two numbers multiplied together, x times y equals our number n. And n is the number that we are interested in. Well, we want to know, is n prime or is n composite? Well, if x times y equals n, then you could rewrite that as y equals n divided by x. And for the moment, let's think of x and y as being real numbers. Then we could graph y equals n over x, and it would look like this. Okay, for some constant n with x and y as variables, we would get this graph on our x-axis, y-axis. Now, if n is a prime number, that's fine. That would mean that all the points on this, if it's prime, then all of the points on this line will have non-integer coordinates, or at least, sorry, they would never both have integer coordinates at the same time, which is what I meant. But if, perchance, there is a point on this curve that has integer coordinates, so let's call them a and b, right? Then that would mean that a times b equals n, and if a and b are both integers, then it would be a composite number, right? Because a and b would be divisors of n. Now notice that this curve here, y equals n over x, it's going to have a point right here, which is on the line y equals x. And if y and x are equal to each other, it's like having x squared equals n, and so they would have to equal the square root of n. So as you can see here, I have plotted, this would be the square root of n on the x-axis, and this would be the square root of n on the y-axis. So this point right here is when x and y are both equal to the square root. And so if you draw lines, draw a horizontal line and a vertical line, you'll see that no matter where this point is that has integer coordinates, if both of these coordinates are integers, no matter where it is, whether it's up there, whether it's over here, or whether it's right there, at least one of the two values has to be less than or equal to the square root of n, right? Like either if it's up here, then a is less than or equal to the square root of n. If it's down on this segment, then b is less than or equal to the square root of n, right? Because you're never going to get a point which is up in this area where, and I'm not circling the y equals x because I'm drawing attention to that. I'm just circling this region up here. You're not going to get a point up there where they're both larger, and you're not going to get a point, anywhere else. So there's a theorem, then, that we can write to kind of sum this up, which says if n is composite, then n it's going to have a prime divisor, in particular, which will be less than or equal to the square root of n. So if we want to look for prime divisors, if we want to look for prime divisors of a number, all we need to do is search up to the square root of n. And then if we search up to the square root of n and we don't find any divisors, then we can say that it's prime. So you can check to see if something's prime by checking all the numbers up to its square root and not exceeding its square root, and see if any of those are divisors. And if none of them are, then it's prime. So that idea is going to be incorporated into an algorithm that was developed by a fellow called Eratosthenes. This is the Sieve of Eratosthenes, and it is a process. It's called a sieve because it filters things out. You throw a bunch of numbers into it, all the numbers up to some maximum number, which I'm going to call capital M. You throw all the numbers in there, and then the composite numbers filter through, and all you get left inside the sieve are just the prime numbers. So we're going to start with a list. I'm going to write this as an algorithm in pseudocode. We're going to start with a list, and it's going to be the numbers starting with one. Not starting with one. You can see I wrote the number 1 and then I crossed it out. Not 1. Let's just skip 1 and start with 2. So 2, 3, 4, ... all the way up to capital M. All right, capital M. We're looking for all the prime numbers less than or equal to capital M. So we've got the list of all numbers that are less than or equal to capital M. We're going to do something. We're going to basically throw all these numbers into the sieve, and then anything that's composite, it's going to drop out of the sieve. We're going to remove it from the list. and then the only things that are left in the sieve when we're done should be our prime numbers. So what we're going to do is we're going to have a counter, we're going to have a variable that kind of iterates through this list, and it's going to be called n, okay? And we're going to start at the beginning, so we're going to start with n equals 2. Then what I want to do is actually do a while loop. I'm going to be increasing n. I'm going to be moving through the list here. And what I want to do is do while n is less than or equal to the square root of m, whatever that is equal to. Now this might be like an irrational number, in which case it couldn't equal that because n is never going to have a value other than an integer. But as long as we remain less than less than or equal, then it's going to continue. And what we want to do, and I'm just going to kind of write the gist of it here. You might want to actually write a function to do the next step, but I'm just going to describe what it is. The thing we want to do is essentially remove from our list all multiples of n from the list except n itself. So basically what I mean by that is saying, remove any kn, multiple of n, kn, for k greater than or equal to 2. All right, that's what I mean by that. So we're not going to remove n from the list. So 2 is going to remain in the list, but any multiple of 2 is going to be removed from the list, any higher multiple of 2. So what we're going to do next is iterate n. We're not going to iterate it by, and iterate means like move it along, like proceed through the list. But we're not going to do that by moving to the next number. We're not going to add 1 to this. We're not going to just add 1 and get 3 necessarily. We're not always going to add 1, because it could be that the next number, like when we get to 3, adding 1 would give us 4, but that number 4 has already been removed from the list. So what we really want to do is just redefine our n to equal the next number that's still in the list. Okay? And then, when we're done, all numbers still in the list are prime. How do we know that? Well, because as we move along, what we're doing is we're removing multiples of our numbers. So we're removing the composite numbers, right? And what we're left with is just the primes. And then when you move to the next number in the list, that's actually guaranteed to be a prime. Because, like, say you remove all multiples of 2, and then you remove all multiples of 3. You're not going to encounter 4 because it's already been removed. The next number you'll encounter is going to be 5. Right? And if the next number is not a prime, well then that's a contradiction, because you must have removed it. If it's not prime, it must be a multiple of one of the smaller numbers, and so you couldn't encounter something that's not prime. So yeah, so this is a really clever idea. Now, I've written this out in like sort of pseudocode, a kind of hand-wavy pseudocode, because I didn't really explain how exactly this happens. But I think that serves to kind of explain how the algorithm works. And I do want to show you in the textbook this example of performing the algorithm with finding all prime numbers less than or equal to 100. So first you throw all the numbers from 1 to 100 into the list. In fact, actually, I would say you don't really put 1 in there, because 1's not gonna count. So then what happens? The first thing you do is you look at 2. And you're going to remove from this list all multiples of 2 except 2 itself. So they indicate that with an underline in this example here. So all the multiples of 2, all the even numbers you can see, which are nicely arranged in columns, every other column is even. So all those even numbers have received underlines, which is like removing them from the list. Now we just have the odd ones. So then you move on to the next number that's still in the list, or in this case, the next number that's not underlined, which is 3. And now we're removing all multiples of 3. So there's all the the 6 and 9 and 12 and 15 and 18. Those are all getting an underline now as well, which means they're being removed from the list. Now the next number you move to would be 5, like I said. Here's 5. And then we're going to remove all multiples of 5. They're going to get an underline. So here's all the 10s and here's all the 5s that are going to get another underline. And then you do it with 7. You get to 7 and say, all right, 7, let's remove all multiples of 7 except for 7. And we've done that. But then that's as far as you need to go, because the next prime number that you would encounter, it would be 11. You don't need to remove multiples of 11, because 11 is greater than the square root of 100. Right? So as once you've removed the multiples of 7, you can be guaranteed that all the remaining numbers, which you can see here, like 2, 3, 5, 7, 11, 13, 17, 19, the numbers that are still in the list, right? Those numbers are guaranteed to be prime numbers at this point. All right? You've removed any other number if it were, they forgot to make 43 green. But any other number, if it were composite, it would have a divisor less than or equal to the square root of 100. Right? So it would have been a multiple of one of these primes that we already looked at, 2, 3, 5, or 7. So that's Sieve of Eratosthenes.